It is my pleasure to introduce Jason Armstrong. He did his undergrad at the University of Waterloo in environmental resource studies and ecology, and then started working at the Royal Ontario Museum as an educator in a variety of topics, including astronomy and evolution, geology, ecology, and the environment. But he spent the majority of his career at the Canada Science and Technology Museum, where he is right now, working in education, the exhibits and exhibitions, energy literacy, and other partnerships. And he's currently the manager of science communication and partner projects, and is here today to really, we're both here kind of with the interest of not only the science of climate change, but also how that science is being communicated to the public. And Jason's an excellent person to broach this topic because he spent his career thinking about science communication and working in science communication. So it is with pleasure to welcome Jason, and I will be moderating the questions and then chiming in at various points if with the discussion, but otherwise, take it away, Jason.
Thank you, Jeff. Thank you, Maura. So again, yeah, my name is Jason Armstrong. I'm with the Canada Science and Technology Museum, which is one of 3 museums here in the National Capital Region that all fall under the name Ingenium. So it's science and tech, agriculture and food, and aviation and space. As Jeff mentioned, I've been working in science communication. I'm going to be talking to you today about climate change and energy, but I just wanted to stress that I am not a climate scientist. So I will try and answer any questions, but on some of the specifics, I'm giving us quite a broad view of how we got here and where we might be going. So just want to start, but since the 1800s, so in the last 220 years, it's been the most complex time in human history. We have had an explosion of knowledge and an enormous growth in population. That means that we have more people connecting with other individuals across the planet, exchanging ideas and growing our collective knowledge. Right now, the phone that you have in your pocket has more computational power than was required to land on the moon in the late 60s and early 70s. And this collective learning has a snowball effect. There's been rising complexity. And with that, we've been using energy and industrializing in new and innovative ways. But this has also come with a cost. There's been increase in weaponry, mounting nationalism. World War I saw 15 million people die, followed by the Spanish flu, which saw 45 million people die. 70 million or more died during World War II, and we've just had the COVID pandemic, which has resulted in more than 6.5 million deaths. So with this increased complexity comes great things, but also does come with some consequences. So yeah, here's a population graph that I'm sure many of you have seen of human population over the last 12,000 years. And so you can really see very, very slow, small growth until pretty much about 1700. We only reached 1 billion in at the, I think it was 1804. And this is the current population today. So I took this off of Worldometers, 7.9 billion people. And if you watch this counter, we should be reaching, I believe, 8 billion later this month. So it's going up and it's still continuing to grow fast. So how do we get here where we're talking about climate change? Well, again, I'm going to go with very high level. I'm sure many of you know this, but just to kind of put the whole thing into perspective. So carbon dioxide is one of the primary atmospheric gases that insulates Earth. Other things that also contribute to the warming of the Earth's atmosphere include things like water vapor and methane, as well as some other different human-made compounds like CFCs, chlorofluorocarbons, or HCFCs. Now, this was actually it's not a super new concept. It goes back nearly 90 years. A gentleman by the name of Guy Callendar, who was an English inventor, In 1932 or 1938, he predicted that the rising levels of CO2 would correlate to rising temperatures. At the time when he released this theory, most of his colleagues were skeptical, but he continued advocating for this until he died. It wasn't until 1958 that another scientist, Ravel, decided that we should be measuring CO2 levels constantly. And so measurements have been taken on one of the observatories in Hawaii since 1958. And it has shown a steady, a seasonal variable, but a steady increase in CO2. Now, the graph here that I'm showing is just showing where we, that really before 1850, there was not very much CO2 going into the atmosphere. And as you can see, down to 2020, we're at more than 35 billion tons annually. And if that seems like a lot, yeah, it is. Even if you look at 2000, so only 22 years ago, it was under 30. So it has increased rapidly, and it continues to increase rapidly. Now, where does this carbon dioxide come from? It mostly comes from our energy use and the burning of fossil fuels. And specifically, if you look at the different sectors, industry and transportation are nearly equal globally. They make up, about 55% of the CO2. Residential, so what we're responsible for heating and cooking and maintaining our homes is about a quarter of it, and then that other quarter is sort of divided up into a number of other different sectors. Now, let's go into that a bit more. Well, we are really good at burning fossil fuels for a wide variety of different things. Here in Canada, over 6 million people use natural gas to heat their homes, also to heat their water in their hot water tanks, to cook their food, and increasingly, natural gas is also used in other appliances like clothing dryers. We also, use fossil fuels extensively for transformation of metals from ores into the raw products before they go into finished products. So currently, less than 30% of steel is made with electricity and arc furnaces, and more than 70 is processed with coal that gets transformed into coke. There's also a ton of different industrial processes that we use fossil fuels for, whether that's making cement or fertilizers or plastics and different petrochemical processes. So really, there is an enormous amount of fossil fuels that are used as an energy source for these things. And as I said, also, the other half is transportation. So we move things, and this is generally based on oil byproducts. So we do have some biofuels, but that makes up a minor percent. So a typical barrel of oil gets taken and then processed into a wide variety of different products. So for land transportation, that's mostly gasoline and diesel fuels. For air transportation, that's things like kerosenes and airplane fuels. And then for transportation and oceans and lakes, that's mostly heavy oils or bunker fuels. So there's different fractions of that one barrel of oil that get produced into those different components. We use the majority in land transportation. So what we actually need to do is take the oil and do a process called cracking, where we actually can rearrange the molecules so we end up with the octanes and things that we want to be able to power our cars. Now, what else is happening is that globally, since the 1800s, we have been destroying carbon sinks. And we keep replacing them with things that are producing more carbon dioxide. So the top picture there is a shot of this is from last year, the Amazon. So it shows existing forests in the green. The yellow is deforestation since 2018. And the red dots are fires that have broken out, which is kind of a new thing in a lot of the Amazon. The picture on the to the right of that is showing what a lot of Ontario might have looked like, say, in the 1820s, when we began having European settlers coming into the province. All of southern Ontario, so you think about the GTA up to up to the Georgian Bay and over to Lake Huron would have been immense old growth hardwood forests. But they're also on some of the richest agricultural land in the province. And so those forests would have been cleared. Same thing would have been happening here in Eastern Ontario. If you drive south towards Cornwall or Brockville, you get into that flat plains, very rich soil, which would have supported these huge trees. Those trees needed to be, or those trees were replaced, cut down, and turned into agricultural lands. Not only were they just cut, but then they were generally burnt. So the process would have been to cut down these trees and then feed them into fires, and then take all that ash, collect that ash into large pots and slowly percolate water through it. And that process gives something called potash, which makes sense from the name. And that potash would have been the first fertilizers that would have been spread on these fields. So how do we know this? There's a couple of different ways. So the below graph is showing data that has come from ice cores in Antarctica. So we can see that in the last 800,000 years, carbon dioxide has risen and fallen steadily from anywhere between 190 parts to about 280 parts. But really in the last I'd say 200 years, we've gone from lower 200s up to right now where we've surpassed 400. In 2021, we were at 415 parts per million. And the graph here that you can see on the side, that is the data that is being collected by the observatory in Hawaii, where you can see the little ups and downs. Those are your seasonal variations as plants take in carbon dioxide through different seasonal variations, but you can see a steady march up. So again, how do we get here? Well, for much of human history, we've been relying mostly on wood and forests for combustion. So whether that was directly burning the wood or often taking that wood and turning it into charcoal. But there has been some history of coal mining. So the earliest references go back over 3,000 years. And there's evidence that first coal mines were in China about 3,000 years ago. By 200 BC, China was using coal for heat and also as a trading commodity. And it was also vital to their metallurgical industry, which first began to flourish in China around 120 BC. So we're going back, 2,300 years at this point. The Romans also were recorded to use coal fairly extensively. After they invaded Britain in 43 AD, they discovered coal fields in Britain, and they realized that coal was superior to charcoal for both heat, for heat. During the Roman occupation, coal was used to heat baths and for ornaments, and also in iron forging. It was used in religious ceremonies with the worship of the goddess of wisdom, Minerva. As part of the worship, the Romans had a perpetual fire at the temple of Minerva in what is present-day Bath. After the Romans left, coal use declined, but it was still being used in England all through the Middle Ages. In fact, some of the earliest evidence that we have of measures being taken to combat coal pollution were in 1306, when a royal proclamation was issued in the city of London that banned artisans and citizens from using coal in their furnaces or in their fireplaces. And coal would remain a problem in England for the next 800 years. Coal pollution would remain a problem for the next 800 years. Now I got these pictures here up on the screen. And this is one of the importance of where coal production really took off. So one of the problems with the coal fields in England was that they would fill with water. And so you could only go down so deep and access coal before basically your mine flooded. In 1812, Thomas Newcomen invented this machine that's here on the side. It was the first steam engine. And the steam engine was horribly inefficient, So it burned a ton of coal to make the steam, but the purpose of it was to pump water out of coal mines. So it had access to cheap and easily available coal. By pumping water out of the coal mines, it opened up vast reserves, and that coal was able to begin fueling the Industrial Revolution. So in Canada, where do we stand? Well, Canada ranks 13th worldwide in its coal consumption. We don't use coal a lot here for, obviously, for heating. And 15 years ago, we still had quite a bit of coal-generated or coal-fired electrical generation. But right now, that coal use is mostly the result of production of coke for the smelting of iron ore. So, for example, British Columbia has some really high-grade coal reserves, and 27% of the energy that British Columbia produces is in the form of coal. They only burn 2% of it, and the other goes internationally to be used in steel production. Coal is a big deal. Based on our current reserves that we know are out there, we have enough coal that we can continue to burn it at the current levels for the next 1,200 years. The issue is not peak resources, as in the 70s, there was a lot of talk of peak oil or peak gas or peak coal. We know now that we have access to enormous amounts of fossil fuels. So it's not the peak resources that are the problem, it's how much CO2 can we continue to emit into the atmosphere before we alter the climate to catastrophic proportions. Now, this is a little bit of my own pet peeve here, but so we are definitely influencing the climate. But I'm going to quote a comedian who some of you might know, George Carlin, and he had a skit where he said, "The planet is fine." And it is true, the planet will be here. The planet has been through a lot worse than us. The planet's been here for 4.5 billion years. We definitely can see evidence of life for the last 3.5 billion years. And we've been here 200,000 years. We've only been engaged for heavy industry for a little over 200 years. And the planet has been through many different things. This is an image, an artistic image of the asteroid crater that would have been left after hitting off the Yucatan Peninsula. That asteroid was about 10 kilometers in diameter, wiped out huge amount of different species of life, probably up to 70% of the different species, and life continued on just fine. So the question isn't whether the planet will be fine, it's whether we will be fine. And that's why I take umbrage sometimes when I hear people talking about we need to save the planet. It's not about saving the planet, folks. The planet is going to be fine. It's us and the other ecosystems here that we've come to rely on that we need to look out for. So one of the ways that we can define this current age that we are in is the Anthropocene. And the Anthropocene is basically what we're looking at is if there is intelligent creatures here in 5 million years, whether that's humans or whatever we've become in that time, or if aliens land on the planet and we're long gone, and they begin looking into the geology and the rocks and the planet, would they be able to see our effects? And there's a couple of different candidates for why we've entered the Anthropocene. So definitely one of them would be CO2. So if they were looking in ice cores that went back, you would see a huge spike in CO2, which would give you a clue that something was happening here. Another clue could be radioactive materials in the form of, say, strontium-90. These are long-lasting radioactive chemicals. The first incidence of those that would occur in the crust was the day of the Trinity nuclear test in the 1940s. You also might, an alien might look and find layers of plastic, steel, concrete that would have been incorporated into rock from the massive urbanizations, megacities, and growth in population that we've seen since the 1960s. But I've heard another great candidate for how we could see the Anthropocene, and that would be in a layer of chicken bones in our time. So right now, as I said, we have nearly 8 billion people on the planet, but on any day, there are about 23 billion chickens alive. It is the most common terrestrial vertebrate of our time. So those are going to leave a indelible mark in the fossil record as well that also is going to indicate that something was happening here. So yeah, the Anthropocene has been an interesting time in human history. Prior to the 1800s, most of us would have been peasants. Maybe 10, sometimes 20% of the population would have been considered wealthy, but the rest of us would have been farmers or peasants. Now, if you have $20,000 a year, you are part of the global aristocracy. Most of us, or I'd say probably all of us, live better than Louis XIV, the Sun King, would have lived at Versailles in terms of the comforts that we have in our daily lives. Now, we have done this by exploiting energy, and energy is one of the ways that we can really increase our standard of living. So there's a lot of places in the world that still need to do a lot of work to actually increase their standard of living. So this is what this picture here is showing change in energy demand between now and 2040. So you can see certain areas, US, Europe, Japan, are actually going down, but many places in the world are actually needing to increase their energy usage. Now, one of the reasons is energy use definitely relates to GDP and a lot of other markers for human well-being. So you can see that if your energy a kilowatt per capita is lower, and so these are all data points of different countries, your GDP generally is correlated with that. And the higher your energy use, the higher GDP. There's definitely very clear correlations between energy use, life expectancy, infant mortality, education levels. So the more access we have to energy, generally, the better things are. Unfortunately, though, most of the energy that we've been using in the last 200 years has been producing this carbon dioxide. So where do we go from here? Well, some people have proposed that we are at something called the 21st century bottleneck. So, it's can we get through the next 80 years and get into the next century without destroying ourselves? We have wealth disparity. We have environmental degradation of oceans. We have desertification. Extinction rates are going up. Climate change is leading to things like migration, famine, and that can also lead to regional and global conflicts. And so we have a lot of challenges here, but all is not lost. So when we talk about the future, what do we generally see? And if you think about the shows that you've been watching throughout the pandemic on Netflix or Prime or HBO, there is a lot of stuff that talks about the future, and it is always these science fiction scenarios. So the first one that I'd say that is very common in the discourse right now is this apocalyptic view of where we are going. Sea levels rise, ecosystem services are compromised, the oceans acidify, food and water systems are shifted, leading to wars, and basically a shutdown of the whole system. It's a pretty grim outlook, and I think it's one that definitely is not empowering. And personally, I think that humans, we're a lot tougher than maybe we give ourselves credit for sometimes in these scenarios. Humans are incredibly intelligent. We can be very cooperative and collaborative when we want. We're hard to kill, and we work really well in disturbed environments. I would argue that we are nearly one of the kind of cockroaches of the mammalian species. So the other option that I see sometimes in these narratives is that we will have a controlled descent into simpler ways. So like I was saying before, if we go back 200 years ago, most of us would have been farmers or peasants. Back in that time, it took about 80% of the population to grow enough food for the entire population. So 80% provided the food for 100%. Right now, because we have access to cheap and plentiful energy, the world population, 100% of the world population gets fed by about 4% of the overall global population. So maybe some of these scenarios look at how do we use our energy more effectively? How do we live simpler lives with less automation, maybe less consumerism, and less population? So it's about how do we bring our population down over the next 200 years to something that might be more sustainable, like a 2 to 3 billion level, while still maintaining a lot of the things that we would like to maintain, such as access to healthcare and education and information. And then the third most prominent one, and it's one that I see a lot of, is also this technotopia. The technology is going to save us. And because I work at the Museum of Science and Technology, I'm going to talk a little bit about this. I don't necessarily think that it is the panacea technology, but it is definitely the one that is, I'd say, the most hopeful. So to do, really combat climate change, we're going to need to move our energy systems from fossil fuel based to much more electrification. And that is happening. And it's happening actually at a faster rate than we predicted 10 years ago. The price of renewables has dropped more dramatically than expected. Solar power costs about 80% less today than it did a decade ago. And if you look at wind energy, about 12 years ago, when Ontario was developing a lot of new power projects, wind power projects, the cost was estimated to be about 28 cents per kilowatt hour. At that point, they were also paying much more. Some of you might remember that because they had a feed-in tariff. So they're trying to encourage the industry. They were paying nearly 80 cents, but the cost of production was about 28 cents. Right now, there's companies in the world that are able to bring their generation costs down to about between 2 to 4 cents. And that's actually cheaper than it is to install new coal production. So definitely wind and solar have really increased in the proportion of energy that they produce, but it's still a small portion. And there still is a question of intermittency. So what do you do when the sun doesn't shine and the wind doesn't blow? So all of this, more energy. We need to be building energy at an enormous rate. And Jeff and I talked a bit about this. Because of all of the infrastructure that you need to build this energy, you actually need to be taking a huge amount of resources out of the planet. So the World Bank estimated that to get to a fully renewable system by 2050, here's what we would need. So these numbers they're actually kind of mind-blowing. 38 million tons of copper, 40 million tons of lead, 50 million tons of zinc, 162 million tons of aluminum, and nearly 5 billion tons of iron. So this transition is not going to come with its own costs. Other things that we're going to require to do as we try and take the CO2 out of the atmosphere are massive reforestation projects. Trees not only capture and sequester carbon dioxide, they also help by shading areas and reducing heat islands. They act through evapotranspiration to put moisture into the air, which cools things. They help with stormwater management, erosion control, and also provide habitat. Then we get into some more, again, science fiction options. So there's been more recently some discussion of solar radiation management. How do we protect the Earth from the sun's rays that are getting in here? This graphic here is showing two different options. One is to use high-level balloons that pump basically aerosolized sulfur dioxide. Sulfur dioxide also comes from things like volcanoes, and we can see that when volcanoes erupt, that sulfur dioxide can lead to dimming of the sun's rays, which will actually produce lower temperatures on the Earth. So that would be, it's actually a very easy, we could do it with today's technology and relatively inexpensive. Another technology that's just recently gotten some coverage is using salt water. You basically take the salt water, atomize it, and spray it up, and small salt crystals move up into the clouds, increase the brightness of the clouds, and increase albedo. Danger with this, of course, is we don't know what actually would happen in the long term with some of these solutions. There's also carbon capture and storage. That's something that a lot of the a lot of people are interested in. There's been a lot of money put into it. Shell Canada had their first successful carbon capture storage project in the oil sands in 2017. Over the course of the year, they put 1 million tons of carbon dioxide into the rocks. But just to put that into perspective, that same year, Canada emitted 573 million tons. So, they put in 1 ton and we emitted another more than 5 million tons. And just also to remind ourselves that Canada is only producing 2% of global emissions. So, yes, it's a good thing that we've learned, but not necessarily the be all and end all. Another solution that has been proposed would be seeding the oceans with iron. Iron is often the mineral or nutrient that is limiting for plankton growth. So I basically grind and pelletize iron, spread it out into the deep ocean. It stimulates plankton growth, and then that plankton comes back down, falls to the bottom of the ocean, sequestering it. So those are just some various ideas about where we might be going. And I'm hoping that, Jeff, you and I can talk a bit about how we bring people along on that conversation. But I'm going to stop it there and just open it up for anybody else who wants to ask any questions.
Yeah, thanks, Jason. We don't have any questions in the question area yet, but hopefully somebody will, decide to ask some questions that we can hopefully answer. And I was just kind of while we wait for some potential Q&A activity. I'm certainly not an expert on many of the geoengineering options that we're throwing around in the community to think about this, but I was fascinated, like, in thinking about this for classes, and also just leading up to this, with the cloud the cloud cooling idea by pumping stuff up. And it's interesting to think about, in that particular situation, whether just the sheer volume of water that we introduce into the atmosphere, how much of an impact that might be, because of the change in albedo, but then we're also introducing a warming effect by having much more water vapor in the atmosphere. And again, I know you're probably not an expert, but that's the one kind of question that always, that comes to my mind. And I'm sure people have done some engineering on that, or some modeling on that.
Yeah, no, I did just read a study on this within the last couple of weeks, and it was some information that was released on a test project, I believe was out of Australia. And yeah, they were finding a net benefit. The increase in the albedo in the clouds was enough to offset the effect of the moisture in the air. And I guess the moisture in the air, generally, it comes out of the clouds faster than the salt does.
Okay, interesting.
But yeah.
So we do have some questions. So I'll read those out. So there's one question about 5 million. So I guess there's missed in terms of thinking about how much resources we would need for our alternative energies, and it was 5 billion tons of one material, which I think
iron.
So I was going to say iron.
Iron is one of the big ones, and so whether that's for your electrical transmission systems, I think, Jeff, you had the number. What is one?
So when I teach, I keep it kind of more down to like a single wind turbine, and a single wind turbine takes 335 tons of steel, which would be one of the main uses of the iron, about 5 tons of copper, 1,200 tons of concrete, so that's cement and aggregates that we still need to generate through extraction from the earth, 3 tons of aluminum, 2 tons of rare earth elements, and then a whole litany of aluminum, zinc, and molybdenum, and other things that go into it. So it's a considerable amount of material. And in fact, on an interesting note, I had students where I was before in Wisconsin actually calculate for the largest wind turbine, largest wind farm in Minnesota, which at the time had 137 turbines. If for some reason we had some apocalyptic nightmare that wind farm was covered with, say, volcanic ash or something, could we actually use that wind farm as a mine, basically, and remine that? It turns out it would be economic to actually go, but there's so much metal used in that wind farm that it would be 100% economic to go back in post-apocalypse, post pretend apocalypse, and actually remine that area for the materials, which is fascinating. So we have a follow-up question here too. So with all the energy inputs to build a wind or solar, how long for earning that back in terms of energy? Ooh, that's a good question.
I used to know this as well because I worked on an energy exhibition, but it was about 10 years ago. I'm just going to look it up right here to see if I can find that and see if I can find it. But it was not as long as I thought it would be.
Yeah. And I think even probably, well, as you look it up, I'll just say, you know, we're starting to get into better and better efficiencies with all of this technology, which is always a promising thing. I know people in, don't totally quote me on this. This was just a news headline I just recently read. I think it might have been Norway that they're achieving practical 30% efficiency in solar panels right now. So there was theoretical over 30%, but now they're actually, you know, they've got practical applications for 30% efficiency, which is pretty impressive. So with those increased efficiencies, that time to pay back is going to shorten as well. And so while you look at that,
So I'm finding, so one of the things that I am finding, and this is, it doesn't actually talk about the time, but it's basically, it's saying that it's how much energy you get back out of it versus how much you put into the production.
right.
And so
right.
it's the return of energy. So wind is at about 18 times. So for if you get 18 times the amount of energy out of that wind power over the course of its life compared to what you put into the manufacture of it.
Right.
So what you would need to do then is look at what the lifespan of some of these technologies are.
Right. So, okay, just following up with some of the Q&A questions. So what should I study in university to be able to help create renewable energy sources, such as hydro, or is it a program outside of school that teaches about renewable energy sources? Well, you know, being at the university, I can answer this. The obvious answer is like some form of earth science. We have many programs that link not only like the pure science kind of aspect, but also linking to the business side of things, so the economics of this. So anything in terms of earth and environmental science is generally a good thing. And I always like to make the plug to students or people thinking about this is we absolutely need scientists. There's no question, you know, scientists are, you know, working on these problems are absolutely critical, but we also just need people that will have a scientific background in, you know, some kind of scientific background in positions kind of like Jason, you know, at museums, but also in areas like government and law and policy, areas that are driving policy. I think the more education specifically, rooted in this earth and environmental science in those places is only going to help us. It's great for people to take advice from scientists, but having that background yourself is always a good thing. So yeah, I would say, go ahead.
No, I was going to say as the same thing, echo that, Jeff. Like, obviously, if you're doing core research in, increasing the efficiencies, there's definitely some science and engineering there. And there are a number of different courses, and I think Carleton actually offers some in specifically renewable energies, does it not?
Yes.
Maybe it's a master's program, I believe. It's kind of multidisciplinary. Yeah. But you also have, to Jeff's point, these companies, they need people who know finances. They need people who know how to do the marketing of this and how to communicate this and how to lobby government. And so there's a place for, I'd say, everybody's education. And if it's something that you're interested in, I'd say look at what your strengths are, what your interests are, and how you could support those, the companies that are out there, the industries that are out there, achieve greater penetration in the market.
Mhm. Yeah, yeah, absolutely. So yeah, just being, yeah, just getting, I think you have, if you get into those roles, I think you're going to, at least from the kind of selfish perspective, you'll definitely find employment, which is a good thing. And then, getting involved in the bigger problem solving aspects is is great. So there's a few other, go ahead.
Yeah, I was just going to say, there. If we go back up to the second question, there's one.
Oh yeah, yeah. How important or useful will small innovations like in stream, excuse me, power generation or snowmaking in the Himalayas to create small synthetic glaciers for water sources? How might this help in smaller communities, or do we have to upscale everything?
That's a good question. I mean, I think I am a believer in the power of the individual and families and communities to have a role in this. Um, and I think it definitely depends. There's many different scales, and I think that every scale is actually important at this time. So
Mhm.
when I went to university way back when the Earth was cooling, the expression was think global, act local. And I think that this point where we are at with climate change and a lot of the issues that are facing the planet, it's we need to think global and also act global. And we need to think local and act local. We need to do them both because really change happens very much at an individual level and within communities. But I think communities also need that support of larger governments and even, uh, government, like the IPCC, so the International Panel on Climate Change, where many countries are coming together and signing these agreements and ratifying them and all working together. So that's really important. So those things are great to scale up, but I don't think ignoring the um, small wins and successes that communities can do, often that makes them much more resilient as well. So
Yeah.
just some of the examples, whether you're talking about in-stream power generation or other projects that are looking at food security or water security. Yes, these things have great effects on climate, but they also actually have very tangible effects in making the lives of the people in those communities better right now. So I say it's win-win.
Yeah, yeah. And even in industrialized areas, like, just from a perspective of being, self-sustaining, if everybody had solar on the roofs right now, things like, the couple of storms that we've had over the last couple of years in Ottawa, with broad, power outages across, the whole region. Not only are you doing the things that, we want to do, which is, think globally and acting locally, but in the end, it benefits you as well because, hey, you don't have to deal with a power outage because you've got your solar on the top of your roof. So there's definitely like wins across the board for yeah, making these making smaller projects work. It's definitely a good
There's a
thing.
great comment that basically says something, it's like, oh yeah, energy independence, green jobs, increased sustainability, healthy cities, cleaner water, like these are all the benefits of what we're talking about. And somebody in the audience is like asking questions like, well, what if we're wrong about this climate change and we do all of these things just making the world a better place? It's like, yeah, that's okay. We can do
Yeah.
that. I mean, if I look at my own life, in terms of small scale, I live about 5K from uh, where I work at the museum. So, I walked home from work yesterday. Well, great. It's better than, driving my car in, or I could bike in. So yes, that's going to reduce my carbon footprint. But you know what else? It's going to give me like 5K of exercise. And if I did a couple of meals a week where I've reduced my beef consumption, okay, so that's great in terms of my emission profile. But you know what? It's also probably good for saturated fat for my heart. So there's a lot of these things that actually are directly beneficial to the individual and have
Nice.
these other planet helping effects.
Yeah. Yeah, I moved to the end of the light rail extension, in the Southern Light Rail extension, so that I don't have to commute. And it's not, yes, it's a good thing, of course, for the environment and public transportation, but 15 or 20 minutes of stress-free time to myself on the train on the way to work, both ways is, I'm looking forward to that aspect of of the commute now, instead of having to deal with traffic. So yeah, personal benefit is nothing to, nothing to sneeze at. Coming back to the questions in the chat here. There's a nice question. It's good that we're working on the technology to have sustainable energy to save us. But you mentioned that many countries do require energy consumption, and most developed countries might not share them, or might be able to, but not share them with those developing countries. The reasons could be associated with politics, profit, cooperation, etc. Is there anything we could do to help them, in your opinion?
Well, yeah, I mean, and this has been actually some of the a sticking point in some of the recent negotiations around this, because a lot of the developing world is saying to the industrialized world, like, you're the ones who, the last 200 years of your industrialization has caused this problem. You profited from it. You're now able to make this energy transition, and we need some help. So I mean, I'm not sure. I think the thing that you can do as an individual is express that view to your government. If that is something that you want to see Canada to stand up for, of some of these technology transfers, or the sharing of these technology, I believe it's going to be essential, because it is, as you mentioned in my presentation, there's a huge demand for energy in a lot of the developing world. And I think it would be not only irresponsible, but I'd say morally wrong for Europe and North America to say to other regions of the world, you can't have what we have and what industrialization has given us, whether that's transportation and refrigeration and heating and cooling and the lighting. Those things are, I'd say, essential for a lot of these regions. And so if they're going to get there and they're not going to do it on the with fossil fuels, then there's definitely going to need to be some assistance. It's going to go back and forth.
Absolutely, yeah. Same thing with, like, water technology, everything. There's so much that needs to be shared to make it sustainable for the whole planet. So what's another question here? What is your perspective on the role of nuclear energy as part of the solution to climate change? I have some opinions, but I'll let Jason start.
I have some opinions too, and again, these are my opinions. I don't necessarily represent Ingenium or Carleton, but I think the nuclear energy plays a big role in a decarbonized energy system. It is great in terms of base load. So here in Ontario, depending on the day, like 50 to 60% of the electrons that are kind of flowing through your light switch when you turn it on are coming from nuclear facilities, which are non-emitting. As well, Canada has some of the largest and most rich uranium reserves in the world. So we have this here. And finally, I'd say that the Canadian nuclear reactor designs, the CANDU reactors, are some of the safest in the world. And I know that there is, concerns around what do we do with the waste afterwards, and that is not something that I would say is we still need to tackle that. And there is some there's 2 communities in Ontario right now looking at deep geological storage, but we still haven't figured that out. But I do think, in terms of just providing a base load for when the sun isn't shining and the wind isn't blowing, it could be very, very helpful.
Absolutely. And again, I don't speak for Carleton specifically, but I think Jason and I have never had this conversation either, but I'm in 100% agreement that I think we need to be using nuclear reactors much more, globally. There's inherent risk in everything that we do, and nuclear energy is not immune to that. But I think when you look at a lot of the the sort of terrible things that have happened to nuclear energy, it hasn't been really the fault of the actual reactors and power plants, their engineering, because engineers are really smart and they do a great job of this. It's generally stupid human mistakes, often for economic or political reasons that lead to major disasters. Like Fukushima, the Fukushima disaster being, of course, the most recent major issue. It's actually really fascinating with that GE reactor. This happened after the large Tohoku earthquake off the coast of Japan in 2011. But that reactor was actually engineered to withstand a 7.9 magnitude earthquake, and it excuse me, 7.9 or 8.1, one of those two numbers. Don't quote me 100% on that. I could call it a teaching slide, but I won't. But it actually withstood a 9.0 earthquake. It actually did fine in the earthquake itself. There was no problems with that reactor. It outperformed its engineering rating. But what the problem was the energy company put it right on the coast in a known area where tsunamis would actually inundate the ground or the land at that part. And it was the tsunami, overwhelming, the protections that were in place for tsunami that doomed that reactor. So honestly, if they had to put that reactor 100 meters above where it was, there would have not been a Fukushima nuclear disaster, because it withstood that earthquake just fine. It was just, again, I don't know what whether the political or economic factors that went into the actual dropping that thing where it was, but what a silly place to put it, quite frankly. Just human error led to that disaster. So yeah, and with CANDU reactors being some of the safest, I think nuclear energy is such a great source for non-emitting energy that we're crazy to not use it more. Even with the waste products, and France has done a lot of work on waste products and reducing those and reusing the rods, and they're actually just producing very small quantities of waste, really highly radioactive waste product, but very, very small quantities compared to most other countries. So there's definitely, and again, if we think about even modernizing things even more with respect to nuclear, I'm sure technology and modernization could help out with that, some of those issues as well. So yeah, I think nuclear is a great option.
Yeah, I mean, there's some actually interesting developments happening now in Canada. There's been some approvals, or they're looking at them with Natural Resources Canada on small modular reactors, and that's also a lot of communities in Canada, which maybe us in the south don't see, but a lot of the northern communities run on diesel generators as they aren't connected to an electrical grid, or just other remote sites, mining operations in that are kind of off grid, rely on a lot of need energy. So nuclear, like small modular reactors that are the size of sort of a couple of shipping containers, can provide access to energy. Also,
Right.
and the other thing I'll say, nuclear reactors do is in Canada, or have, is produce a lot of isotopes that are used in medicines, whether it's medical imaging or treatments of different things. So
Yeah.
there is that other side of it that we often don't see. We think about the and the effects can be terrible. Don't get me wrong, but the when they're properly mitigated by, like you said, scientists and engineers who are doing their job and not being interfered with, then it's relatively safe.
Yeah. We use those isotopes in earth science too to actually date minerals. So yeah, cool. Okay, another question here, and we're approaching the hour, but I think we both have a little bit of time if needed. But please speak to the use of hydrogen to turn steel and concrete processing to net zero. I don't know if you have much knowledge on.
I have no information on this. Do you, Jeff?
I know an extremely small amount in terms of steel, and I know that like using hydrogen it cuts the use of it uses like a third of the emissions, or half of the emissions, but it does, of course, it's more expensive, which is kind of a theme, in terms of using at least alternative energies when they first get started. But yeah, I don't know, I don't know who's doing it. So yeah, I really don't know. It's probably something I should look into for, like, I'm kind of later in the term or something when I'm talking about energy a little bit later. But
Yeah, and as yeah, I can hydrogen makes sense for both of those uses. I mean, concrete
yeah,
is also it's concrete is a big because you need a lot of heat, right? So basically, you're taking things like limestone and
yeah,
and heating it, and decomposing that structure, and you need huge temperatures, and so that's generally done with natural gas.
right,
Which is again better to be done with natural gas than coal in terms of its emission profile. But still, when you look at also the building and that's happening across the planet, and the urbanization that's happening in many places, and the need for quality buildings, we're going to need a lot of concrete.
yeah, and steel. Yeah, both of those
Yeah.
things.
Oh, yeah.
Absolutely.
Exactly. Yeah. I mean,
Yeah, yeah,
I guess I know that steel there is looking at it in terms of using electricity, so that you can do arc furnaces and things like that. But I'm not sure if that's applicable to all different types of steel.
yeah, yeah. It's definitely an area I don't have very much knowledge in. Apologies to the question asker. And then down the end, there's some cool experimentation with tidal energy generation happening in the Bay of Fundy at Parsboro.
Yeah,
Yeah,
that Canada has, I think, I'd have to check it out. I did a couple of years ago. I know that we had one of only two functioning tidal generation stations in the world. France had the other one. Bay of Fundy was the second. And I know that there were some projects happening, I believe, in South Korea, and I know that there's some proposals for a big project in the UK as well, up between Wales and England. But yes, there's some of those have been traditionally more where they actually block off sort of an estuary, right? And then they use the difference to basically run. It's nearly like a hydro facility that runs in two different directions depending on the tide.
right.
There's also been a lot of research I know done in the Bay of Fundy in recent years on tidal turbines that actually just sit, that are anchored on the bottom of the ocean floor. The benefits there is that they don't impact habitat as much. And you can, there's a lot less infrastructure cost to them. So yeah, I mean, there's some enormous potential in tidal. I know that it's also really challenging. Salt water is terrible for a lot of the different metals that go into these operations. I know we have actually on the front lawn of the Museum of Science and Tech, there's a tidal turbine that was used in testing in the Bay of Fundy. And it eventually was actually damaged by the intensity of the tides there. So that's also the robustness of these machines is something that they're working on.
Yeah, yeah. Salt water is tough.
Yeah, yeah. It corrodes things. It likes to eat things.
Yeah. I think we hit all of the questions in the Q&A, and
I think you did.
yeah, unless anybody has anything else, I think we've gone a little bit beyond our hour, but I think it was a fascinating hour.
Yeah.
I think a lot of issues that are raised, but I think walking away from it, I think the point, that we all, there's some big problems, but we all can help solve these, again, whether they're at the small scale, actively using small scale technology, or implementing small scale changes to our lives. But then, yeah, getting involved, and thinking globally, and thinking about everybody on planet Earth. I think that, I think the George Carlin idea is great. Yeah, the planet's totally going to be fine. I mean, in fact, the planet's probably better off without us. The reality is, and I think ultimately humans will be fine, but will it be the 8 billion-ish humans on Earth that will be fine, or is it going to be, you know, a drastic reduction in population, you know, and it's you know, survival of the species at a much smaller level, you know, in the future because of climate change is an interesting question to think about. But yeah, until Elon gets us all over onto Mars, I think we need to really be focusing on Earth.
Yeah. No, I agree. I would say that over, the course of my career and studying, doing environmental studies in the early 90s and first hearing about climate change there, after my first year of university and all of the different courses I took, I got to say, I was it was grim. I was depressed by what I had learned of the state of the planet. And, in my time since then, I'd say I'm actually much more optimistic in terms of in human ingenuity. And that's what I was kind of referring to. As much as 8 billion people is a lot of people, when there's these critical numbers of just people talking about ideas, and the more people you have, the more interesting ideas. And the fact that we have all these communication technologies that, people can communicate their ideas from, anywhere on the planet right now because of, access to technology, which is becoming more and more ubiquitous. And so there are good ideas floating all around in places that maybe would never have heard those voices 50 years ago. And as we saw, I'd say with the response to even just global pandemic, when we want to come together and get something done, we're really good at it. Yeah. So I'm actually quite optimistic that we have the skills and we have the tools, and now we just need to kind of work around the how. But that's we always get there.
Yeah, I agree. I too am optimistic. Well, thank you very much, Jason. And with that, thank you everybody for joining us. And for those of you who are watching after, hope you enjoyed.
Yeah, I'd like to thank everybody, the participants who joined us, and Carleton for inviting me to speak on this. It's been very nice.
And thank you both for participating today, and thank you, the audience, for joining us. Quick reminder again that this content will be posted as a recording to the Faculty of Science website, and we will be sharing the recording out, the link out with everybody that registered today. So again, much thanks. This topic is not exhausted, certainly, and I think that we could build a series out of it. So hopefully we'll be able to connect again soon to talk. Thanks. Enjoy the rest of your afternoon.